So, well, first of all, I want to say, like Johan said yesterday, that I really enjoy going to the Nordic Optical Telescope to observe. This is like a little romantic movie here of one of our recent runs at the telescope. I like working with the staff, and having your own telescope sort of is operating yourself is really rare, and that's really fun to do. So the FIES spectrograph was not built. I didn't know there was sound here actually, but this is great. So the FIES spectrograph is not an ultra-precise radial velocity spectrograph. That's not why it was built. It was built basically as a high-resolution spectrograph, and it was moved from the telescope onto its own building to sort of make it more precise in 2006. It's not it's temperature controlled, but not like at the millikelvin level that these kind of telescopes are. It's really loud, and it's also not in vacuum, which is also really important. So really, it's a challenge to do these super precise radial velocities, which normally people spend years and years on developing these precise instruments. So I'm going to go on to the next slide so we can get to credit. Phew. Okay. So just to set up sort of why we want to do more precise radial velocities, the idea is that we want to try to characterize the environments of these small planets that have been discovered with Kepler and TESS, and figure out what the diversity of these planets are that are sort of smaller than Neptune. There's a huge amount of planets between the 1 Earth radii and 4 Earth radii that do not exist in our own solar system. We know very little about them, whether they're sort of scaled up as super Earths, or if they're maybe water worlds, or maybe they're sub-Neptunes with a thick hydrogen-helium atmosphere. And in order to do that, we really need to measure their masses, and thus with the radius measurement from TESS and Kepler, we can get the bulk density. We really need precise velocities, I say here, of a few meters per second in order to do this kind of science. So we wanted to try to aim at a few, which was kind of a slushy sort of goal for FIES, which is quite ambitious, I would say, even though people are now routinely doing 1 meter per second with their ultra-precise radial velocities, and even below. And because of these hardware upgrades, we got finance for the telescope. There was a NASA and the Transiting Exoplanet Survey satellite, the TESS satellite, asked to finance some observing time at the Nordic Optical Telescope to follow up the targets. So that resulted in a 90-night program, half of which was Danish national program, and the rest was sort of a NASA-funded program, which I think is rather unprecedented that NASA, which usually uses money in space, finances follow-up observations on the ground outside the US. At least I don't know of any other situations where that has happened. So the idea was to follow up all these planets discovered by TESS. And here's a sort of a overview of the upgrades we did. And this is not what we did. This is when FIES was moved from the telescope onto its other building, and I think that's a younger Jacob, looking very confident about the situation. Overconfident. Anyway, it went well. So we installed an octagonal fiber feed at the telescope, which is crucial. I'll come back to all these things. We also put in a pressure chamber around the grating, and then we tried to install the Fabry Pro Etalon calibration source in order to calibrate the spectrograph. So before I get to that, I want to say that optimizing a spectrograph for precise radial velocities is like a board of nails. In other words, if these represent uncertainties, there's some systematics in the instrument, all different kinds of sources, we need to pound down all these nails all the way down into the board to really get a precise radial velocity. If even one just is still sticking up, then we really haven't improved anything. And so when you want to go to lower and lower and more precise radial velocities, your board expands sort of exponentially. You get more and more nails. And sometimes this happens. You try to pound down the nails and you can't, or you might even have the wrong tool. Maybe you have a hammer and you need a screwdriver. So it's very difficult, and you don't know how many nails there are because you can't see them before you pound down the other nails. Okay, so you get the analogy, I think. So one of the most crucial things to start with is getting an octagonal fiber feed, because if you have a circular fiber and you position the star in the fiber, the way you position the star gives enormous radial velocity drift. So if you just put the star a little bit outside the fiber, you can get hundreds of meters per second RV shifts. So with our new fiber feed, we try to move the star, which is the black spot, the fiber, which is the black spot, out of the star. And if you squint, you might be able to see the exposure meter and sort of the level going down here. So you can really see we're pushing it out several, I think 1.5 arc seconds outside the star. And then we tried to look at the radial velocities. And so this is the corrected radial velocities for a standard star, which behaves very well and is very bright. And you can see the RMS of these observations, where we really, do this quite dramatically, much more than you would do normally when you observe, do not affect the radial velocities at all. So I think we're rid of this sort of positioning issue, which is really crucial to get rid of, because that's almost impossible to calibrate you out of. Second thing we did was to install a pressure chamber around the grating, because the atmospheric pressure changes, that changes the index of refraction. So we really have a very, very large and expensive barometer sitting on the mountain, and we wanted sort of to get rid of the atmospheric influence. And so this is the grating of FIES. We were told we cannot really get a new grating, and if you kind of touch the grating, you ruin it basically. So that would essentially ruin the spectrograph. So we were very worried about getting this out. And this is Niels Christian and Michael from our institute. And Niels Christian is fantastic. He not only did he build sort of the pressure chamber, but he also built a tool to lift the grating out of its box. So this little thing is engineered, and all these little thingies that are there are sort of lifting it up. They're turning and then lifting it up, so they can very carefully take the grating out and put it in its pressure chamber here and install it back into the spectrograph. So now we're kind of not affected by the changing atmospheric pressure of the Earth, which changes quite dramatically, as you probably know. This is just from the Nordic Optical Telescope's weather page, and this is sort of a year of atmospheric changes. And you can see here in, I think, microbar, the changes, and you see there's the diurnal, which is a tiny little thing going on, and then this rest is just weather systems coming in, and they will result in many, many hundreds of meters per second radial velocity drift. So now we are rid of that, because this plot shows you this is not that long, but it's like 15 days or so. And now we're in millibar here, so you see we're in tens of millibar. And the blue curve, I apologize for the sort of busyness of this plot, but the blue curve is actually the atmospheric pressure, or the pressure inside the chamber. The red and the yellow curve is the temperature. So basically what we're seeing here is the gas law. So the pressure doesn't, well, it changes because of the temperature of the grating changes. So we're not now affected by the outside atmospheric pressure. So that seemed to work well, and we were really happy with that. The last thing we tried was the Fabry-Perot etalon. So this is basically a calibrator that gives very uniform calibration, so sort of nice and uniform peaks all across the spectrum that we supposedly know where are, so we can calibrate the spectrograph, rather than using the quite difficult thorium argon lamps. And this is the etalon without its cladding on, so it looks fairly complex, and it is. And then here it is final installation in the FIES room inside its box, cooled to millikelvin precision, and it's really a nice piece of technology that will give this calibration source. And we had a sort of a laser-pumped light source going into the etalon, so we could get lots of light into the spectrograph, lots of calibration light. And here's an example of why we want to do this. This is a thorium argon calibration image. This is a full raw CCD. You can see all the nice little thorium lines here, and you can see even the well-behaved ones, you kind of see scattered light and bleeding when you get to the brighter ones. And the problem with thorium is that it has very ununiform illumination. You have some very strong peaks, and then you have a forest of much smaller peaks, so you really need to expose a lot, but that means that you get a lot of bleeding. And up here in the very red part, you see argon lines that completely saturate and dominate the spectrum, an enormous amount of scattered light. So they're not very good to work with, but that's what we have or had. And then we tried to install the etalon, and this is the same picture. Now with the etalon, you see the nice, well-spaced peaks all across the spectrum, uniformly illuminated, and really much, much better to work with, if we knew where the lines were. Which is, I'll come to now, I think. This is Asia. But even with the etalon, I'll say FIES is super difficult because the spacing of the orders is very, very tight. So this is up in the red, and it's a bit difficult to see, but these are the stellar observations, so the star spectrum, and next to it is the etalon. You can see here, when you go into sort of the redder part, this is a zoom in, so that's the star, and this is one etalon line, and you can see it's basically overlaps. It goes into the stellar spectrum over in the red, so we have an extreme tight spectrum, so we had to work very hard at getting out the scattered and sort of bleeding light that came from this calibration source, and this must be removed, and I think we actually came to a place where we did this extremely well. So this was not the issue. It could be done, but it took a lot of work, actually. So traditionally, what we have done to calibrate these radial velocities, because the instrument, the temperature is controlled, but not at the millikelvin level, as I said. So actually, it breathes. There's a sort of a systematic floor, a 0 point, if you will, that the spectrograph floats around with and changes. We want to try to calibrate that. So traditionally, we took a thorium argon just before the science exposure, the star, and we took the star, and then a thorium argon after, and then we sort of interpolated between those, sort of figure out where the spectrograph, the drift of the spectrograph at that moment, and remove that such that we just see the star's velocity. And this is, again, a standard star, and these are some observations over, about 20 nights or so. And it's hard to see here, but the RMS of these observations is about 8 meters per second. So that's not what we wanted. We wanted something, and this is before we did any work. So this is, well, it's before the etalon. So it's after the fiber feed and the pressure chamber, but it's before we use the etalon. So this was kind of what we could do. Sometimes we were lucky, maybe 5 meters per second over a short period of time, but usually something like 10 meters per second RMS, which is just too big an RMS to do these small planets. You can then only more or less do hot Jupiter type of mass measurements. But we used the etalon, and this is some of the first work we had. So this is again a standard star here, HD 10700, and this is 1 night of observations corrected with the etalon. And the amazing number is right here, 0.8 meter per second RMS over these observations. That's outrageously good. Much better than we had expected, and we were super happy when we saw this. And spoiler, it does not continue, unfortunately. But this was really amazing. We could actually, within some hours, calibrate, and underneath here, I should say, the spectrograph is drifting at, tens or hundreds of meters per second during this. So we're really correcting quite a lot, a factor of usually 100 to get to this sort of precision level, because FIES is not as stable as other spectrographs. So we were super happy and hoped that this would go great, but then we extended this observation to a longer time period, and this is the same sort of calibration with the etalon. Now, again, a standard star. We were hoping for just a straight line, but we see this kind of drift and then something going on here, and now we're back to an RMS of almost 8 meters per second, back to where we started, basically. So we were scratching our heads trying to figure out what was going on, and the idea with the etalon was that we knew that etalons also drift, but we had a laser that could beat with one single of the etalon lines to understand where that line was. We knew the separation between the lines, so if the whole spectrum kind of drifts, we would know where all the other lines were, and we could use that to calibrate the spectrograph. And when we talked about this, I was like, but what about, is there no inter-peak drift? I asked the people, no, this does not happen. However, this is exactly what happened. So the community, and this was, to be fair to my colleagues, nobody was really expecting this kind of issue, and now these etalons that are on all these precise radial velocity spectrographs have this enormous issue of chromatic drift, which is really horrible. So in fact, what's going on is that the spectrum is not just drifting, it's kind of going like this, if you can see my fingers, so the lines are sort of moving apart in a chromatic fashion, which is horrible for calibration, of course. So this is from Espresso, and this is their etalon. What you're seeing here is several representative colors across the spectrum, and you're seeing the drift of that part of the spectrum as a function of time. So this is nearly a year, and you're seeing sort of the red drifting, and it's not linear, you can see. It's sort of bending, and the purple, is different. It jumps there, and then there's the blue here, and the orange, and the green. And this is the full drift of the etalon. So the etalon is drifting, and then it's sort of having this chromatic thing going on, which is shown up here, at the same time. So that's super horrible. You won't be able to use an etalon for any calibration. And I don't have a plot here of this, but I've seen images from the NEWIT spectrograph, which is also one of these next generation spectrographs that has an etalon, and we see 10, 20 meter per second drifts, chromatic drifts, and they're nonlinear and they're complex, like super complex curves on the order of timescales of 2 or 3 months even. So it's really quick, and it's very large amplitudes. Mind you, we're trying to do meter per second, or even NUIT is trying to do sub-meter per second. Having this issue is really unfortunate. So the etalons at this current stage are not really working as we hoped, and we don't exactly know why. Probably it's the cavity, it's the light inside the cavity that is, the cavity sort of is seemingly being larger and smaller at different wavelengths because of deterioration of the coating of the cavity inside the etalon. That's the best explanation currently for this, which is quite unfortunate. So the only other option is a laser frequency comb, which is quite expensive and probably not within the budget to get to the Nordic Optical Telescope for FIES, I'm afraid. Or maybe it is. If somebody has $1 million, let me know. So what did we then do? Well, we tried to sort of use the thorium argons, which are still, so the etalon is much better at calibrating, as you could see, for a single night. But if we could sort of figure out how the etalon was drifting, we could maybe solve this issue. So down here is the result of that attempt. So this is the data I showed you before with an RMS of about 8 meters per second. You can actually get down to 3 meters per second. But then again, this is a very short time scale. So on longer time scales, we get this very chromatic drift, and then basically all bets are off. So we're unable to use the etalon as calibration, at least at this time, for FIES, and basically every other spectrograph in the world. So it's not just the spectrograph at FIES. Okay, 3 minutes, really? That's 17 minutes I've spoken. Oh, so 20 minutes. Okay, I see. I thought we had 25 minutes. Okay, so here's I want to show this because I think this is kind of interesting. So we tried now, we had the etalon, which on short time scales doesn't drift, and so we have a lot of light. So we're able to take very quick measurements of the etalon. So basically what you're seeing here is the spectrograph drifting. This is meters per second, so this is fairly well behaved over some hours. You see like 30, 40 meters per second drift. And what I tried to do here, if I zoom in, is sort of try to simulate if we did this sandwiching mode that I talked about in the beginning, where we take a thorium argon before and after, and then the stellar exposure in the middle, and sort of interpolate and try to figure out what the drift is. So that works in most cases. For example, so if you look, if you look up here, this is supposed to be a thorium argon here, and this is supposed to be another thorium argon, and in between you're doing the stellar exposure. So if you take those two and interpolate linearly between them, you get the red point. Now, but what we in fact did was use the etalon to see how the spectrograph is drifting. That's all the blue points. And if you integrate over that, you get an orange point, which is nicely situated behind this red point. So in this situation, it's great, right? But if you go to a situation like here, take a thorium argon, then you do your stellar exposure, and then you take your other thorium argon, you linearly interpolate, then the spectrograph would be there. But in fact, what goes on is that you have this upward motion, and then you have a downward motion. So in fact, the integrated actual 0 point of the spectrograph is there. And there's a quite big difference, as you can see. And we don't know what's going on because we have no calibration while we're doing the exposure. So the average error in this case is about 0.5 meter per second we're doing, but the maximum error is 2.5 meters per second, even on a short 5-minute exposure. But it gets worse than that. This is another example where we tried. Now you see on very short time scales, 120 meter per second drop, and then a reversal in the 0 point of the spectrograph. And up here, when we're doing linearly, you see here's the thorium, and here's the other thorium, and here's the sort of the middle point. They look very similar, but then you go to this point here. This is the thorium, and that's the other thorium. And you have this very nonlinear behavior. The interpolated point is here, but the actual drift of the spectrograph is here. So that's a huge difference. The maximum on this plot is 12 meters per second. And the average is about a 3 meter per second error. So we're really not calibrating very well. Another example where we have 200 meter per second drift over some hours of the spectrograph due to some temperature probably. And we again see large errors because of this sort of sandwiching effect that we have. And I'll spend the last minute just saying why we may think that is. And this is sort of a diagram of FIES from above. And here's the spectrograph. And you see these 3 heaters that are situated above the optical table with fans blowing around the air. And the idea is to try to keep sort of the spectrograph at a stable temperature. But this is run by a very old PID loop, and nobody really understands how this PID loop works. And probably what's happening is these heaters are sort of fighting each other, injecting heat into the optical table, into the spectrograph, which then sort of breathes thermally and moves apart, resulting in quite rapid very rapid and many timescales drifts of the spectrograph that are very, very difficult to sort of calibrate. So I'll skip that, and I'll just go to my conclusion slide, which is basically this. If you take a 1978 Ford Fiesta, you add nitro fuel and a brand new Mercedes engine, you don't get a Lamborghini. So, in other words, taking an old spectrograph, trying to put in some new fancy stuff, and then expecting that it runs like a super precise, ultra precise spectrograph built for that reason is extremely difficult. That is the lesson learned. It's not impossible, I guess, but you can do upgrades, but it's very difficult to do this, especially from remote, when we're not actually in the lab with the instrument, and through the staff at the telescope who are also running a telescope simultaneously and having to operate and take care of all the rest of the community. So that was all for me. Thank you.